video, I want to talk about steady states in CSTRs. So, steady states in CSTRs. And so basically, look at these curves we've been looking at with the conversion from the mole balance and the conversion from the equilibrium balance. In CSTRs, they can have more than one intersection, and so if there's more than one intersection, then the reactor has multiple states where it can operate. So going back to this energy balance, UA over FA naught TA minus T minus the sum of theta I CP T minus T naught CPI minus the heat of reaction X is equal to 0. And then let's just say that this is equal to Cp naught. Then this can be rewritten as Cp naught UA over FA naught Cp naught. That's multiplied by TA plus Cp naught T naught minus Cp naught UA over FA naught Cp naught plus 1 multiplied by T minus the heat of reaction X is equal to 0. So then we can just make up some variables to kind of simplify this equation. So first of all, I'm going to say that this UA FA naught Cp naught is kappa, and that kappa TA plus T naught over 1 plus kappa is equal to Tc. So if you do this, you can rewrite this equation as minus X heat of reaction is equal to Cp naught 1 plus kappa over, multiplied by T minus Tc. So then X is equal to Cp naught 1 plus kappa multiplied by T minus Tc over the heat of reaction, and T, like if we solve this for T, that's equal to Tc plus the heat of reaction X over Cp naught multiplied by 1 plus kappa. So then this is the energy balance for a CSTR with the heat exchange. So energy balance for CSTR with heat exchange. So then using the CSTR mole balance, which if you remember, that's X is equal to minus RAV over FA naught, because V is equal to FA naught X over minus RA. So this is just the mole balance. We can plug this into this equation for X. So if we do that, we get the minus RAV over FA naught multiplied by the heat of reaction is equal to Cp naught 1 plus kappa multiplied by T minus Tc. So then this equation, this is known as G of T, or the heat generating term. And this is R of T, or the heat removing term. So to analyze the multiple steady states in a CSTR, we want to plot R of T and G of T on the same graph as a function of T. So I'll show you an example of that. So I'm going to erase some stuff real quick. So I'm going to actually rewrite this equation. So minus RAV over FA naught multiplied by the heat of reaction is equal to CP naught 1 plus kappa multiplied by T minus TC. And then this was G of T, and this was R of T. So then if we start plotting these, so we're plotting this as a function of T. So this one is R of T, and this is T. So this will just end up being a straight line. And if you increase T naught, then the line will move this way. So this is increasing T naught. And then you can also look at what happens if you change kappa. So this is R of T and T again. So if kappa is equal to infinity, you end up with this. So this is kappa equals infinity. And so let's say kappa, this is kappa equals 0 right here. So, and then as you increase kappa, you'll start seeing this. So increasing kappa. So then let's look at a plot of G of T. So this is G, T, and that's going to be more of a curve, so maybe something like this. And so this would be low, E, and then maybe you have a curve down here. This would be high, E. And then you can also look at what will happen if you increase tau. So let's say, I'm just going to draw some curves. So this will increase. So this is increasing tau. So then let's just look at how these look on a plot together. So if you plot both R of T and G of T, so let's say that this curve is G of T, and then this is R of T, and let's say that you're increasing the temperature. So all of these points are potential steady states. So you can see where if you have this T naught, then you could potentially end up with several steady states, whereas if you use this one, you potentially only end up with one. So you can see that if you're operating your reactor at too low of a temperature, it might not be able to reach a steady state where the conversion is higher. So then you can kind of look at these steady states. So let's say, you have entering, let's say these are your entering temperatures. So you have T01, T02, T03, T04, T05, and T06. And then these are your reactor temperatures for the entering temperature. So reactor temps. And so for T01, maybe there's only one possible temperature that the reactor can operate at. But then maybe for T02, there's two, so TS2 and TS3. And then maybe for temperature 3, you have three possible steady states, so TS4, TS5, and TS6. And then maybe for 4, you also have three, so TS7, TS8, TS9. Maybe for 5, it goes back down to two possible states, so TS10 and TS11. And maybe there's only one possible state for a really high temperature, so maybe that's way up here somewhere, so then it's only crossing in one spot, so then say that's TS12. So then you can plot these and you can get what's called an ignition extinction curve. So I'm going to erase some stuff real quick and then plot that. Plot this, you have T0 on one axis, TS on the other axis. So let's just say that this is T01, T06, so then you have this steady state temperature with this T0, and this will increase up to here. And so this is 1, 2, 4, 7, 10. And then this can jump up to here, so let's say that's 3. So this is 3, 6, 9, and I'll explain all this in a minute. 12, 5, and 8. So these are all of your potential steady states with the entering temperature. So for instance, if your entering temperature is T01, you only have one potential steady state. But if you have 2, then you could potentially have this steady state or this steady state. So basically, as your temperature increases along here, it will continue to increase until you get to T05, and at that point, your reaction temperature will jump to 11, to whatever this temperature is. And so this is called the ignition temp. And so if your reactor, say your reactor's operating at this temperature, and you start decreasing the temperature, then it would drop all the way to here, at which point anything below this temperature, it'll drop down to here. So that's called the extinction temperature. So I'm going to erase this real quick and then show you another way that you can look at this. So let's say you have R of T and G of T versus T. And so let's say this is 0.4. I should have drawn the curve first. So say you have a curve like that, so that would be g of t, and then r of t looks like this. So right here, g is greater than r, and then this is, let's just say this is TS7 right here, and then say this is TS8, and this is 9. So then you have, so then at this point, let's just call this point 3, g is less than r, and at this point, just call that point 2, g is greater than r, and at this point, point 1, r is greater than g. So these points 5 and 8 are unstable steady states, and the reason why they're unstable is because, so for instance, if you look at point 8, so if you slightly decrease the temperature, then the heat removing, there's more heat being removed than heat generated, so the temperature would continue to decrease until you get to 7. Whereas going the other way, if going this way, then the heat generating curve, the heat generating is greater than the heat removing, so the temperature will continue to increase until you get to 9, so because you would land up here. So basically, if the temperature, this point would be considered unstable, because if you move even a teeny bit off this temperature, then it'll either decrease to 7 or increase to 9. Whereas looking at one of these other states, like say 7, if you slightly decrease the temperature, then the heat generating curve is greater than the heat removing, so the temperature will continue to increase back to 7. And the same thing if you increase the temperature, the heat removing curve is, or the heat removed from the reactor is greater than the heat generated, so it'll decrease back to 7. And the same thing with this steady state at point 9, if you slightly decrease the temperature, the heat generated, the more heat will be generated than removed, so the temperature will increase until you get back to 9. And same thing, if you increase the temperature, there will be more heat removed than generated, so it'll decrease back to 9. So basically, if any of these steady states, 1, 2, 4, 7, and 10, or 3, 6, 9, 11, and 12, if you move slightly from that temperature, it'll naturally go back to whatever temperature it was operating at. Whereas if you're at one of these states, these unstable states, if you move slightly off the temperature, then this one, like if you move slightly to increase the temperature, it'll keep increasing until you get to 6, or decrease until you get to 4 if you decrease the temperature. And then this one, if you slightly increase, it'll keep increasing until you get to 9, or decrease until you get to 7.